topic we're going to cover in this set of lectures is what I would term carbonic acid chemistry. We're going to see what that term means as we see the individual components. So, carbonic acid chemistry. This is carbonic acid itself. You can see that it's the parent acid to the bicarbonate and carbonate anions. If you imagine deprotonation of carbonic acid sequentially, that will give you bicarbonate and carbonate, which you would have met before. This is a carbonate, so this is effectively an ester of carbonate, so the R groups would be alkyl or aryl organic components to form organic carbonates, which you can see are very closely related to the ester functionality. Carbamic acid, something that maybe you're less familiar with. Carbamic acid is an amide-like chemical. We did meet it very briefly in amino acid chemistry when we talked about the parent amino acid system. And acarbamate, trivially known as a urethane as well, is a substituted system either on the O or on the N or on both. They would all be referred to as carbamates, but they would be substituted carbamates, and we will see how that comes about later on. If we push carbonic acid chemistry a little further and change the oxygen chemistry on the carbonyl system to 2 nitrogens, this becomes urea, something probably that you're familiar with. Urea is certainly familiar to you as a byproduct of biological systems, of mammalian systems, as an excretory product, and you may have met it within chemistry as a separate chemical. We can substitute ureas, so we can have carbon-based substituents on those nitrogens, either on the nitrogen in one position or 2, and we'll meet that chemistry later. Or, unusually, we can guide the chemistry to substitute onto an oxygen and come to O-substituted ureas, and these are a little less common. Just because there's no other place to put these chemicals, if we carry on the substitution and replace all the oxygens with nitrogen, we end up at guanidine, and guanidine is an excretory product of avian species, and guanidine is an all-nitrogen analogue of urea. And we can have substituted guanidines that appear in nature or are used synthetically. We cover those here because really, so you can see it is an extrapolation of carbonic acid chemistry, but we cover those here because you're less likely to see them anywhere else in the chemistry course. Carbonic acid chemistry drugs, just to put the functional groups into context. This is carbamazepine, which is an anti-epileptic drug, and in carbamazepine we have a urea functionality appended to a heterocyclic system, and a heterocyclic system, you'll remember, is a cyclic carbon system where at least one of the carbons has been converted into a non-carbon atom. This is carbromal, which is a sedative, and carbromal has a urea functionality in it as well. This is a peculiar beast. This is carbimazole, which is an antithyroid drug, and carbimazole has a carbamate, hence the name carbimazole. It has a carbamate functionality in. But if you look at it a little more carefully, it has also a cyclic, because it's part of a 5-membered ring, urea in it, but that urea has had its oxygen changed into a sulfur. Now, because sulfur is in the same group in the periodic table as oxygen, sulfur can substitute for oxygen in systems, natural systems, and in drug molecules, and does so, and we can take advantage of that chemistry for drug purposes. And this is a cyclic thiourea. Okay, we're going to start from some chemistry that I hope you'll have a feeling for, which is the chemistry of phosgene. Now, phosgene is a chlorinated version of carbonic acid, and phosgene is more stable than carbonic acid, and you'll see why that might be the case in a moment. Phosgene was first used in the First World War as a war gas, a toxic gas, and it's toxic because this double acid chloride type functionality hydrolyzes in the presence of water, so water on epithelial surfaces, on surfaces, surface of the eye or the nasal cavity epithelial cells are very moist, and phosgene, if it's deployed as a war gas, reacts with the water and releases HCl. This is concentrated HCl, so it effectively acts by burning the surfaces that it falls on by dehydration when the HCl gets hydrated. This process can carry on, and the equilibria are far over to the right hand side, by the way. They're shown as equal here, but they are actually far over to the right hand side. This process can carry on, and another mole of HCl can be produced. That takes us to carbonic acid, and carbonic acid per se is not a stable species, and in fact breaks down to carbon dioxide and water. And in fact you can look at that chemistry as a reversed process, that carbonic acid actually comes out of the fact that when carbon dioxide is dissolved in water, it sets up an equilibrium which involves carbonic acid. Nature fixes carbonic acid by acid-base reactions to form carbonates and bicarbonates, and that's how carbon dioxide gets fixed in geological or natural terms, nature. Phosgenes, so if we look at the reaction here, this is water acting as a nucleophile towards the electrophilic carbon of phosgene at the carbonyl oxygen. We can have the same sort of chemistry occurring with alcohols, so R groups could be ethyl for ethanol, etc. Alcohols aliphatic alcohols would react like this, and other OH containing functional groups that are alcoholic. We can form ester acid chlorides because there are two acid chloride-like functionalities, and we can use the same alcohol or a different alcohol to fully substitute to a carbonate. So be aware that you can sequentially add alcohols or use two equivalents of the same alcohol to substitute to a carbonate, and that allows us to make organic carbonates. Organic carbonates or organocarbonates are not particularly common in drug substances. They are used in excipients, and there are probably some examples of carbonate-based drugs out there. Not that I'm too familiar with them, but they're certainly out there somewhere. Okay, if we take phosgene and react with ammonia, two equivalents of ammonia would give urea with removal of two molecules of HCl. The amino groups on the carbonyl are not particularly basic, so you don't end up with a dihydrochloride salt. You end up with urea and HCl being given off from the reaction, and urea is a stable covalent white solid, very, very stable organic species. And in fact, if you want to, unlike the carbonic acid chemistry that we saw, if you want to break down urea, because urea is so stable, Nature, if it encounters urea and wants to access the chemistry of urea, for instance, to release the nitrogen as a feedstock for for biological systems, there are enzymes known as ureases which break down urea and hydrolyze it to carbon dioxide and ammonia, and then biological systems can use the ammonia to fix into amino acid synthesis, nucleic acid synthesis, etc. If we, instead of using ammonia as a nucleophile and that reacting at the acid chloride chemistry, and by the way, just a general point, if you're unfamiliar with the acid chloride chemistry, certainly textbooks will cover this chemistry, and I'm sure if you look up acyl chloride chemistry on the internet, you will find resources that will expand on this. We have met the chemistry before, and I have pointed you towards resources that throw a bit of light on the chemistry, so just to remind you. If we use an amine as a nucleophile, we can disubstitute to a substituted urea on the nitrogen, and that would be a primary amine reacting to give a substituted urea and release of 2 moles of HCl. Or we can use a secondary amine, and the secondary amine, if we use 2 equivalents of that, will go the same way, and we end up as a substituted urea that's more heavily substituted. Carbamic acid. Now, carbamic acid, if you take the analogy of carbon dioxide reacting with water to give carbonic acid, then if carbon dioxide reacted with ammonia, you would get carbamic acid, which would be the result of that reaction. As with carbonic acid is relatively unstable, and the equilibrium's over to the reactants, not to the product. But that chemistry can be exploited indirectly. So phosgene can be made to react with an alcohol to give a chlorocarbonate, which is a mixed ester acid chloride type system. And then a reaction with an amine, an aliphatic amine, aromatic amine, will give a carbamate chemistry. Now, the carbamates are very much finding their way into modern drug substances because of this modular chemistry of the variation of R and R1 being easily accessible and exploitable. So the modern formulary, as it develops from your time as students, will certainly contain more and more carbamates as part of the armory of drugs. So what we're going to do is look at a synthesis, and we're going to use carbamazepine as an example. We're going to start a way into the synthesis of carbamazepine from this heterocyclic molecule, and reaction with phosgene would give a chlorocarbamate, a bit analogous to the excuse the siren there, it's like New York. A reaction with phosgene will give a chlorocarbamate, and this chemistry can be utilized by extending it by reaction with ammonia and ethanol. Ammonia as a gas is soluble in ethanol and can form a saturated solution of ethanol in ethanol. Ethanol is not nucleophilic enough to react under the conditions that could be chosen for this chemistry. The ammonia, or an amino chemistry, would be more nucleophilic, and this selectively reacts at the carbamyl acid chloride, carbamyl chloride, to give a urea, and this would complete our carbamazepine chemistry. There is another route which is interesting, and that's using something called potassium cyanate, and in this chemistry the carbon of the cyanate ion is electrophilic, and this is nucleophilic enough to attack that position, and when we do that chemistry and quench the resultant product with water, we get 2 carbamazepine, the antiepileptic, you might want to think how that happens with potassium cyanate. It's an unusual chemistry, but it's worth thinking about how mechanistically you might end up with the product. Push a few arrows and see if you can come to some sort of explanation for that reaction. And we end up with a urea functionality appended to the heterocyclic ring. We're going to choose another example, which is neostigmine. And neostigmine is an acetylcholinesterase inhibitor used for muscle dysfunction. And a reaction of dimethylamine with phosgene can yield a carbamoyl chloride, an appropriate carbamoyl chloride that can be elaborated, made more complicated. We're going to do that by reacting with a aromatic alcohol. Now, phenols at the oxygen are not particularly nucleophilic. This nitrogen is not particularly nucleophilic because of the effect of the aromatic ring on these lone pairs of electrons. However, if we take that chemistry and we take a phenol and react with sodium under certain reaction conditions, we can form a phenoxide. And we've met this, I think we've met this chemistry before in the alcohols unit. And phenoxides are more nucleophilic and can attack the electrophilic carbon at that position. That gives us an intermediate which is then reacted with methyl bromide in a nucleophilic substitution reaction. So our acid chloride has been appended to that oxygen to give this functionality. Then we're going to access this chemistry here. Now this is not terribly nucleophilic because it's tied up in conjugation with this carbonyl fairly strongly. Whereas this nitrogen, even though we mention it's not particularly nucleophilic here, we change the reaction conditions to force it to react with an electrophilic alkylating agent, and we end up with a quaternary ammonium bromide, which is neostigmine, and that's our active drug. And that has a carbamate functionality in it. Just to show you that we can ring the changes on the chemistry and introduce sulfur into systems. We don't have to have oxygen in carbamic acid systems, or as we've seen in ureas, etc. We can introduce sulfur. And dithiocarbamic acid is not particularly stable, just like carbamic acid, but we can stabilize the we can stabilize the carbamic acid by trapping it as a stable salt. In this case, if we reacted this system with ammonia, excess ammonia, we would trap it out as ammonium dithiocarbamate. So this is relatively easy to synthesize from this chemistry if we have sufficient ammonia. And we can also arrange for chemistries to be trapped out as sodium salts if we have sodium hydroxide present as a base instead of ammonia. We won't go into the details of that chemistry, but it's just to show you that that chemistry can be accessed as well. What we're going to look at here is the synthesis of another drug called antabuse. And to access antabuse, this is the chemistry we would use. We use dimethylamine in the presence of carbon disulfide, which is a carbon dioxide analogue, and sodium hydroxide, and that will allow us to trap out the sodium salt of the resultant dithiocarbamate salt. And we do some interesting chemistry here. We take our sulfurs that are still free in our salt, we take 2 equivalents of the salt, and we oxidize this system with a fairly mild oxidant. Chlorine or sodium nitrate in HCl acts as a mild oxidizing system, and notice it's or, not together. So it's either chlorine or sodium nitrite in HCl, acts as a mild oxidant, and allows us to take electrons from this system and manipulate them, and we can form a disulfide linkage. You've seen disulfide linkages within protein structures as stabilizing entities, and this is effectively a disulfide sulfur-based ester. If you think about it, this is a dithioester like functionality here, and we're cross-linking across the free sulfur positions. This is bis diethylthiocarbamoyl disulfide, which is a bit of a mouthful. It's also known as disulfiram or antabuse, and this compound irreversibly inhibits alcohol dehydrogenase, primarily in the liver, and it's used in aversion therapy in alcoholics. It makes alcoholics feel sick when they drink alcohol, because their body then, because of the aldehyde dehydrogenase or alcohol dehydrogenase inhibition, can't cope with the excess alcohol, and emesis ensues, so the patient throws up. Now, when we've talked about phosgene in the chemistry here, the thing with phosgene is industrially or within laboratories, phosgene would be an extremely toxic entity to use. So there are some far less toxic analogues that perform the same functions of phosgene, but with slightly less reactivity, but certainly much more acceptable in terms of their toxicity. And it's an interesting chemistry to look at, because to show you the variety of groups that can be attached to our reactive system, how we can manipulate these functionalities around here to be substituted around our carbonyl in different ways. And these whole groups are effectively leaving groups, like the chlorine would be in phosgene. These things will leave the system under the influence of attack of a nucleophile at the carbonyl. This would be a leaving group in this chemical, and these are much more stable.